Okay, here we have a Brayton cycle, ideal, so no irreversibilities, 10 megawatts. P1 and T1 are given, P3 and T3. So this is it, going into the compressor, going into the turbine. Remember that the heat exchanger has constant pressure, as well as the inlet and outlet, or the Q out, has to occur at constant pressure as well. So 1 to 2 is the compressor, heat exchanger, turbine, and then we Q out going from 4 to 1. Okay, so I have state 1 and state 3. I can go ahead and look up my H values because I want to go ahead and set my states here. So I'll look up H3 and H1. Remember, this is ideal, so 1 to 2 is isentropic, as well as 3 to 4. So I'm going to use PR1 and PR3, right? Because for isentropic, I'm going to use the relative pressure ratio to help me figure that out. That'll give me PR2, which will in turn give me H2. Same thing with state 4. I will calculate PR4, and from that get H4. So let's start by looking up states 1 and 3. This is 300 Kelvin and 1450 Kelvin. So at 300 Kelvin, my H value is 319. My PR value is 1.386. At 1450 Kelvin, I'm halfway in between these two, which gives me an H of what, 1575.57, and a PR value of 522. Okay, so those are those two states. Okay, so H1 again is 300.19, and PR1 is 1.386. H3 is 1575.57, and PR3 is 522. Now I'm going to use the pressure ratios to figure this out, which is essentially PR2 over PR1 equals P2 over P1. Again, this is for the isentropic compressor, right, where the pressure ratio is 1200 over 100, and I know PR1, so from that I can calculate PR2. It's just going to be 12 times that, which gives me 16.632. That is what's going to set state 2. So I'll look that up in a second, but first I'm going to calculate PR4 so I can look that up at the same time. I'm going to use the same idea. 3 to 4 is isentropic, so PR4 over PR3 equals P4 over P3. Again, this is just the reciprocal, the pressure ratio, going from 12 to 1 rather than 1 to 12. Okay, I know PR3, that means PR4 is just 1/12 of that. So divide that by 12 to get PR4, and PR4 equals 43.5. So now, knowing these relative pressures, because of the isentropic process, I can go look up my H value. So we'll start with the 16.6. Okay, so for 16.6, you can see I'm over here just above 600 degrees Kelvin. I can look up my H value is going to be 610.65. Okay. Remember, my other PR value is 43.5, so that's going to be over here just above 780 Kelvin. That gives me an H value of 800.78 when I do the interpolation. So those H values are, again, 610.65, and H4 is 800.78. Set my states. That's the first step. Now I need to find my mass flow rate and my thermal efficiency. Well, here's what I have. Okay, I know the work of the cycle. I know the total work. And I know that equals my mass flow times basically the turbine minus the pump. So the turbine, of course, is H3 minus H4 minus, not the pump, the compressor, which is H2 minus H1. So again here, this is 10 megawatts as given in the problem statement. So I know that. I know all of these H values. So from that, I can calculate the mass flow rate, which is going to be 21.54 kilograms per second. So again, knowing the total work and knowing all my states, I can find the mass flow. Okay. In order to find the thermal efficiency, well, for that one, I'm just going to use the work of the cycle, which again is 10 megawatts, divided by Qin, which is going to be the mass flow times H3 minus H2. Right? That's where Qin occurs. Now I know the mass flow. I can take that. This is 10 megawatts. Plugging in my H values and that, I get 48.1%. So again, just like most everything we've been doing, okay, set your states, which in this case is finding the H values. For the isentropic, you can use the relative pressure ratio to figure that out. Once you've set your states, then just do what it's asking to solve the problem.